Welcome! In this video we complete section 2.2, Proofs about Numbers. We will look at the division theorem and modular arithmetic. So consider this. Any integer a has the form 2q or 2q plus 1, where q is an integer. Basically, this is saying that every integer is either even or odd. So I've expressed my integers relative to divisibility by 2. Either an integer is a multiple of 2 or it is one more than a multiple of 2. Well, I can do the same thing with 3's. Relative to the number 3, every integer in the world is either a multiple of 3 or one more than a multiple of 3 or two more than a multiple of 3. If I kept on going, if I went 3q plus 3, oh, well, that really is just a multiple of 3. We can do the same with 4. Every integer is a multiple of 4, one more than a multiple of 4, two more than a multiple of 4, or three more than a multiple of 4, and so on. Pick any divisor that you want. So 17. It's a multiple of 17 or one more all the way up through 16 more than a multiple of 17. These things that we're adding, the plus 0, the plus 1, the 2, the 3, up to 16, those are remainders. If you divide an integer by 17, you're going to end up with a remainder of somewhere from 0 up through 16. So how to write an integer a in terms of multiples of b in general? I did it when b was 2, I did it when b was 3, when b was 4, when b was 17. Let's express this idea with a generic b. Here we go. This is the division theorem. Given any integers a and b, and we will assume b is greater than 0, there is a unique choice of integers q and r such that, so first of all, a equals bq plus r, and r is greater than or equal to 0 and strictly less than b. Q is really short for quotient, and r represents the remainder. So for example, 17 equals 5 times something plus something. 17 is the a, 5 is the b, so I need my q and r. What is the q that goes there and the r that goes there? So, using just a little guess and check, 5 goes into 17, well, looks like maybe 3 times, but it leaves a remainder of 2. So the 3 is what I put for q, and the 2 works for r. Now, you might say, well, wait a second. It seems like there's lots of choices. 3 and 2 work, but there's other things that work also. Like, what about 2 and 7? This is correct arithmetic, but it doesn't satisfy this second condition. I wouldn't say that 17 divided by 5 is 2 with a remainder 7. I'd really say 17 divided by 5 is 3 with a remainder of 2. So in order for uniqueness, and this is where this unique choice comes in, I have to make my remainder somewhere, it could be 0, but it has to be strictly less than the b. So I need a remainder somewhere from 0 to 4. And that's where the 3, 2 comes in. All right, pause the video, try the last 3, and unpause when you are ready to see the answers. Here we go. 39 is 3 times 13 plus 0. There's a remainder of 0. 17 is 24 times 0 with a remainder of 17. That's okay. And here's the tricky one. Negative 17 is 5 times negative 4 with a remainder of 3. So this remainder, in this case, it has to be, let's see, 5 is my divisor, so the remainder has to be 0, 1, 2, 3, or 4. So you need to figure out the correct q to put in there to make your remainder one of those numbers. Here's a sample proof that one might do using this idea of divisibility. The claim, if n is not divisible by 3, then n squared minus 1 is divisible by 3. So here's our proof. Let integer n be given such that n is not divisible by 3. Then here's our division theorem. By the division theorem, one of three things has to be true. Either n equals 3q, or n equals 3q plus 1, or n equals 3q plus 2 for some integer q. You know, this type of reasoning happens so often, we're going to stop saying the phrase by the division theorem, and we'll just say, yeah, we have a few cases that can be. Since n is not divisible by 3, we don't consider the first case. So there's really two cases. Case 1, if n equals 3q plus 1, then n squared minus 1, so that's the conclusion I'm focusing on. I have to say something meaningful about n squared minus 1. N squared minus 1 equals 3q plus 1 squared minus 1. Work it out, and it looks like there's an expression where I can factor a 3 out. Since that stuff in parentheses, since 3q squared plus 2q is an integer, n squared minus 1 is divisible by 3. Case 2. What if n equals 3q plus 2? Then, again, I take the n squared minus 1, work it out, and we find that we get a multiple of 3. Since that quantity in parentheses is an integer, n squared minus 1 is divisible by 3. And to wrap it all up with a single sentence, therefore, if n is not divisible by 3, then n squared minus 1 is divisible by 3. Alright, so here's a proof for you to practice. Pause the video, give it a try, and unpause when you are ready to check the answer. Let's give it a try. The hint says prove the contrapositive and consider cases. So let's suppose that n is not divisible by 6. Now, as an aside, you wouldn't write this as part of your official proof, but as an aside, now what are you trying to prove? We need to show that n is not divisible by 2, or n is not divisible by 3. Well, if n is not divisible by 6, then n has the form 6q plus r, where that remainder, well, q and r are integers, and the remainder r is from 1 to 5. I'm not allowing the possibility that r equals 0. So I have 5 cases to consider, and I'll try to put these concisely each on one line. If n equals 6q plus 1, then n equals twice a number plus 1, so n is not divisible by 2. If n is 6q plus 2, then I can factor 3 out of the 6q and get 3 times an integer plus 2, so n is not divisible by 3. In the case n equals 6q plus 3, we find n is not divisible by 2. In the case n equals 6q plus 4, we find n is not divisible by 3. And in the case n equals 6q plus 5, we find that n is not divisible by 2. So in all cases, n is either not divisible by 2 or not divisible by 3, as we wanted to show. This proves the contrapositive, and so it actually proves the original claim. Modular arithmetic and notation. Modular arithmetic really focuses on the remainder upon division, like the r from the division theorem. When we write a mod b, that means the remainder when a is divided by b. In computer languages, you often see the percent symbol used as the mod operator. For example, 18 mod 5. 18 divided by 5, let's see, 5 goes into 18 3 times with a remainder of 3, so that's 3. This big number mod 5, well, you know, when you divide by 5, all you need to do is look at that last digit, so that leaves a remainder of 4. 42 mod 7, 0, I can have a remainder of 0. And remember, this whatever I divide by, the remainder is going to be some number 0 up through 6. So it could be 0, and it could be 1 less than the divisor, or anything in between. How about negative 15 mod 3? 0, because 3 goes into negative 15 evenly. Here's the tricky one, negative 14 mod 3. Well, if I did my division theorem, what remainder would I end up with? I'd end up with a positive 1 remainder. 3 goes into negative 14, negative 5 times, that would give me negative 15, and the remainder is a positive 1. Negative 13 mod 3, 2. One way to think about it is that these numbers are increasing. Negative 15, negative 14, negative 13. They're increasing by 1 each time. And these numbers are increasing, 0, 1, and 2 each time. Alright, some problems for you to practice. Try each of these, and when you are ready, unpause the video and you can check your work. Give it a try. Alright, we are back. For problems 1, 2, and 3, the answers are 0, 2, and 2. Let me talk about this third one for a moment. Notice that this 6k squared, that thing is a multiple of 6, right? 6k squared, and 6 is a multiple of 3. So in fact, this guy by itself, that is a multiple of 3. So that has a remainder of 0 when you divide by 3. And so consequently, the only thing that really matters in this whole stuff in parentheses is just the 5. And the 5 leaves the remainder of 2. So you actually can split up an addition and work remainders out separately to get your solution. For the next 3 problems, the answer is false. There's a counterexample. Part 2 is false, and there's a counterexample. And part 3, true. That is a true statement. Alright, so take some time if you need to, kind of look at those solutions, see if you can make sense of that. And that finishes our section on 2.2 and our treatment of the division theorem and modular arithmetic.